Hi, in this video, we want to take a look at different classifiers. So we've gone over several different classifiers so far. And what I want to do, I want to just kind of put them all into one video so that we can take a look. And what we're going to do, we're going to take the football data that we've been using for home wins and away wins, we're going to take a look at using the number of goals scored to be able to predict win or lose. And so we've looked at this data set before. The reason why I like this a lot is that this is a balanced data set. Half of the data is a win, half of the data is a loss. That's just, I mean, not exactly because of ties, but you know, it's pretty close. One thing that we have to consider whenever we do these classification problems, if we were in a situation where we had like credit card fraud, let's say credit card fraud is 0.5%. Well, when I'm in that situation, the vast majority of the data is not fraudulent, but that tiny sliver that is really what we're most focused on. That's called an imbalanced data problem. And the data is imbalanced because there's so many non-fraudulent activities. So we need to first get comfortable with balanced data before we can handle those. All right, so first thing we're going to do, we're going to take the data in the format, and we're going to, if you remember from the data, it has like home team wins and losses and the number of scores. And what we need to do, we need to convert that to the format we want. This portion of code that's on the screen right now just does that for us. So let's get matplotlib, get pandas going. Let's load the actual data. So here we can see, the goals. And what we want to do, we want to convert this into a format that we can do machine learning on for this type of problem. Let's take a look. All right, so now we have our wins and losses column. And what we want to do is we're going to have zeros and ones to represent win-lose. And we're going to take the zeros and ones and we're going to stack them on top of each other. That's what we're doing with the concatenate. Let's go ahead and take a look. All right, so here are the actual number of goals scored. And here is win-lose. So we can see the winning team is always represented in the earlier rows, and the later rows are the losing team. Now, there's only one predictor variable, so this is a very simple data set, but a simple data set is a good place to start. All right, so I decided to do the train test split convention instead of cross-validation. Either way will work. All right, so we're going to go ahead and do train test split. I'm going to put in 60% of the data into training, 40% into test. I'm going to go ahead and set the random state. That way, if I want to do this again, I'll get the same data set later down the road. I put shuffle true just to make sure that everything's mixed up. So since the data is, wins, loses like this, to make sure that there's nothing prone to selecting a certain region of the data, I go ahead and shuffle it. And the stratify, make sure that in my train set, I have about, my train set has the right proportion of wins and loses, and the test set has the right proportion of wins and losing. If I put stratify equals none, it can do just a random grab, and by happenstance, I might get like the train set might be more concentrated on one categorical variable or level than the other. All right, so now we have our train and our test data. So let's just take a look. Not how you spell shape. All right, so here we have one predictor variable and 456 rows in our predictor variable training set. In our test set, same number of predictors, but here we've got 304 rows, 304 observations. Let's do the same, but now let's do the Y. All right, so we can see that we've got a vector of 456 values, and so these correspond to each other. All right, so that's looking good. All right, so now we're going to run through the model building. We're going to do logistic regression. We're going to do k nearest neighbors. We're going to do a decision tree. We're going to do a support vector classifier. Then we're going to do a random forest. All right, so let's go ahead and import logistic regression. I'm going to call log reg to be my logistic regression classifier. Now I'm going to fit it on the training data. Now let's go ahead and run predictions on the training set and on the test set. All right, so remember, when I do metrics on the training data, that tells me how well the model fit on the training data. When I run in metrics on the test data, that's an indication, that's my only measurement of how well the model fit to the population. Training tells me how well does it fit on the sample. Test tells me how well it fits on the population, approximately. All right, so let's get our accuracy. All right, so we can see that we've got about 75% accuracy on our training set. And we have a 76% accuracy. So it's actually a little bit bigger than the train, but not a lot, so I'm not worried about it. Remember, I want to see these two close. If these two are far apart, that's an indication that even if I have a good test score, that's an indication that I've overfit my model. Now let's take a look at the confusion matrix. Okay, so when I look at the confusion matrix, what's going on is there's an and actually on my laptop. Try and get rid of it. All right, there we go. All right, so the rows of the confusion matrix correspond to the model. The columns correspond to what actually happened. So the model predicted 180 losses and 124 wins. And we can see that there were 152 actual wins and 152 actual losses. And so we can see when we look at the errors, so remember the data says balance. Since it's balanced, what I really want to see, well, first of all, I want to see everything in this 130 position, and I want everything in the 120 position. I want to see zeros off that. So there's what we call these two positions, the 130 and the 102, that's called the diagonal. The 22 and the 50, that's called the off diagonal. I want to see 0 in the off diagonal or as small as possible. So here we can see that there were 50 times that the model predicted loss, but they won. We can see that there are 22 times that the model predicted win, but they lost. So we can see that the model predicts losing a little bit more than it does winning. So there's a little bit of, there might be a little bit of bias in this one. All right, let's do this again. So now I'm going to do k nearest neighbors. So I'm going to, from sklearn, I'm going to import neighbors. And we're going to do a 5 neighbor classifier. So remember, when we do k nearest neighbors, I take a data point and I find the 5 closest data points in the training set, and we take the average of those 5 to figure out what our prediction is. So for those 5 points in the training set, we look at is it a win or lose, and then we combine them all together, and it's kind of like voting. Now let's go ahead and fit the model. get our prediction values. And let's go ahead and look at our accuracy. All right, so if you remember, we were in the 70s before, now we're in the 60s. So we can see the k-nearest neighbor didn't do as well. We have a 65% accuracy on the train set and 64% accuracy on the test set. So, well, these two values are pretty close together, so I'm not worried about being overfit on this case, but we can see that logistic regression was the better model. Now let's take a look at this. All right, well, k-nearest neighbor, wow, that's a pretty big imbalance. We have 102 for predicted losses, but they won. We only have 7 predicted wins, but they lost. So why is this important? Well, in reality, like when I make a prediction and I'm wrong, there are different penalties for being wrong. Let's consider these two cases. All right, so the first one's for logistic regression. The second one is for the situation where we're using k-nearest neighbors. Okay, let's say I'm in the situation where predicting win, but they lose is a really bad situation. Like for some, if I predict win, but they lose, then the penalty is worse than the other mistake I can make. Well, in that situation, this 7 is pretty small. Since it's small, that's where I would want to be. Well, why does this come up? Think about that credit card fraud situation. Let's say we build a model. Somebody is attempting to make a purchase, and our model needs to flag them as, hey, fraudulent or not fraudulent. Okay, so now if we say not fraudulent, then the person makes a pays and walks away. And if we say fraudulent, things shut down, it's rejected, and like the bank goes and calls the owner on their phone right away. Well, let's think about the penalty of the two situations. If we're in the situation where we incorrectly say it's not fraudulent, then the customer is going to lose all that money. And if we say that it is fraudulent, but it's not, then we're slowing the customer down and we're harassing them. And we have employees doing, making phone calls that don't need to be made. Or it could be like automated text, thing on the phone. So we have to consider how bad is each scenario when we select the model that we want. We don't just want accuracy. Accuracy is not enough. We have to consider where are the mistakes, and considering the penalty of each mistake, is this model worth it? All right, now let's go ahead and look at a decision tree. So we're taking decision tree classifier. Now we're going to fit the model. So we'll go ahead and get our predictions off the model. Let's compute our accuracy. Now let's compare these two. All right, so it looks like 75 and 76 again. So this is comparable to the logistic regression model. Let's take a look at the confusion matrix. Ah, wow, it's really close to the, is it the same? That is close to the logistic regression values. Yeah, they're exactly the same. Oh, that's interesting. Okay, so here, we can see that these two models are producing the same results. So if I wanted to pick one over the other, I would have to decide what is more valuable to me. Are the stakeholders involved more comfortable with logistic regression or a tree model? Tree model, a human being can look at it and they can figure out the values without pencil and paper. But logistic regression is just taught a lot more. A lot more people are familiar with it. It connects better to like college algebra. So, I need to consider my audience if I want to think about using one of these two models. All right, now let's take a look at support vector machines. So what we're going to do, we're going to make a support vector classifier here. Now let's fit on our training data, make our predictions. Now let's get our accuracy. And we've got 75 and 76 again. Huh. And we got the same exact values. All right, so these 22 and 50 are probably some weird situations. They were probably either really high or really low scoring games. I'll bet you the ones where they predicted lose, but they lost was like a 1-0 game, and the games where it predicted win but it lost, those were probably really high scoring games. And once again, what the difference in points between winning and losing was probably just 1 point. All right, so now let's take a look at random forest. This is the type of model that I go to first for spreadsheet problems. And here I'm going to just set the number of trees down to 25. You know what, I'm going to make this a little bit more interesting. I want something more interesting to happen. So I'm going to put that up to 500. Why? Because I can. And I put random state to 42 for anybody who's looked at Hitchhiker's Guide to the Galaxy. And here we're going to go ahead and fit. All right, so we got it fitted. We get our predictions. Now, let's get our accuracy. All right, and 75, 76. Okay, well, let's see what happens. Exact same values. All right, so let's mix this up. Let's cut this down to 5. I want something a little bit more interesting to happen. All right, so we got a little bit different of values, maybe. Same nonetheless. Huh, that's interesting. All right, well, this is all I've got for you. I hope you're staying safe with COVID-19. Take care and goodbye.